is about temperature and kinetic theory. And so we're going to talk about temperature and heat, the Celsius and Fahrenheit scales, gas laws, absolute temperature, Kelvin's temperature scale, thermal expansion, kinetic theory of gases, kinetic theory, diatomic gases like hydrogen and oxygen, and equipartition theorem. And so the first section of our book is going to talk about temperature and heat. So temperature is a measure of relative hotness or coldness, but really it's a measure of energy. Something that has a little more energy when we touch it feels warm, and what we feel as heat is actually energy transferring from one object to another object, which is our fingertips. So heat is the net energy transferred from one object to another due to a temperature difference. Everything in the universe wants to reach a state of equilibrium, thermodynamically speaking. So if something is warmer in my hand, warmer than my hand, that means it has more energy. So when I touch something with my hand, that energy gets transferred to my hand. If my hand was the same temperature of the object, there would be no need to transfer energy, and it wouldn't feel warm and it wouldn't feel cold. So the reverse of that is if I touch something that has less energy, it will feel cold because the heat energy that I have transfers from me to the object. And so this energy may contribute to the total energy or internal energy of the object. It can also do work, or it could do both. So temperature and heat is based on the total internal energy of an object. So everything in the universe is in motion, and so therefore all molecules have kinetic energy. They also have potential energy due to intermolecular forces, strong and weak force, and the charges of the molecules and spins and all that stuff. So anyways, we're going to focus on the kinetic energy with regards to heat. Keep it simple for high school. So the molecules can move three ways. One is translational, where they just simply slide. The other is a vibrational energy, which is where they oscillate. So their bonds are like springs, and so they can stretch back and forth, so they have a tendency to kind of bounce like this. And then the other one is rotation, so you can have a molecule that rotates around, and you can have a combination of all three. And so all three of those are kinetic energy of molecules or matter. So a higher temperature does not necessarily mean that one object has more internal energy than the other. The size of the object matters as well. Actually, the molecular bonds make a difference too. So when heat is transferred from one object to another, they are said to be in thermal contact. So when I touch something that's hot or I touch something that's cold, there's a temperature difference between myself and what I'm touching, and what I feel or experience is a transfer of energy. The two objects in thermal contact without heat transfer is actually what we call thermal equilibrium. And at some point in time, the whole universe will reach thermal equilibrium. When there's no more transferring to be transferred, then that's it. There won't be any temperature. So then a thermometer is used to measure temperature. Now the way that this works is it takes advantage of the properties of different metals. Different metals expand at different rates. And so brass has a higher coefficient of linear expansion. So when you heat that up, it will stretch more, where iron will not, and it causes it to curl. And this is how the old school thermometers were made. We also have mercury thermometers, and so mercury expands under pressure if it's sealed in an object, and we'll talk about that too. So what are we measuring? Well, what we're measuring is how much something changes or expands. So if we look at water at sea level, for the Celsius scale, the freezing point is 0, and the boiling point, or the point in which it changes to steam, is 100 degrees Celsius. Now the Fahrenheit scale focuses on the same two things, but their freezing point is 32 degrees Fahrenheit, and then the boiling point is 212. And here are two formulas that allow you to convert from Celsius to Fahrenheit and from Fahrenheit to Celsius. So if I take a molecule and the temperature for an ideal gas is held, the temperature is held constant, then the relationship between the pressure and volume is, and this is based on ideal gas law, pressure sub 1 and the volume sub 1 is equal to pressure sub 2 and the volume sub 2 if the temperature is held constant. When the pressure is held constant, then the proportion is the volume of the first object over the temperature of the first object should be equal to the volume over the second object, volume of the second object over the temperature of the second object. And so remember that energy is conserved. And since thermal energy is an energy, technically thermal energy is conserved. That's what all that stuff means. So combining all that stuff together is, we get it from ideal gas law, but your textbook says that if we put those things together, we'll get ideal gas law. But basically, if you take the pressure and you multiply it times the volume, you're going to get a wide variety of things, but there's a relationship between temperature, volume, and pressure. And so capital N is the total number of molecules in a gas. K sub B is Boltzmann's constant, which is 1.38 times 10 to the negative 23 joules per Kelvin. So temperatures, capital T temperature, we need to make sure that it's in Kelvin. So just like length always has to be in meter, mass always has to be in kilogram, time always has to be in second. For our calculations, temperature always has to be in Kelvin. And then we can convert it back. So the ideal gas law is this. You're going to see about 3 or 4 different variations of it. This is the ideal gas law. This is the ideal gas law, but now we go from capital N to lowercase n, and the lowercase n represents the number of moles of a gas, and R is another universal constant, which is 8.31 joules over moles per Kelvin. And so remember, capital N is the number of molecules, and then lowercase n is the number of moles. And so if you're saying, well, what's the relationship between the number of moles and the number of molecules? Well, 1 mole of substance contains Avogadro's number of molecules. So 1 mole of anything is going to contain 6.02 times 10 to the 23rd molecules of something. So, and we call that Avogadro's number because he's kind of the guy who came up with it. So the constant volume gas thermometer is useful because temperature is directly proportional to pressure. When we heat something up, it gets extra kinetic energy, and then it vibrates more. And if you contain that in something, which is where the constant volume comes from, the container doesn't expand. What happens is the molecules bounce off of the inside walls of the container more because they have more kinetic energy. They're accelerated more, so they're going to have more force, which creates more pressure. So if you decrease the temperature, what happens is the pressure decreases as well, as does the kinetic energy. So the absolute zero occurs when there is no pressure, no temperature, and no kinetic energy. Technically, we're focusing on the energy. So there's no internal kinetic energy, and so that's what we call 0 degrees Kelvin, which occurs at, theoretically, negative 273.15 degrees Celsius. And this occurs for all gases, all right? So if I have 3 different gases here, and I lower the temperature, lower the temperature, lower the temperature, they will all converge on this absolute value point. Well, the temperature at which this occurs is called the absolute value, and there's no lower temperature than that because temperature is really a measure of energy, and it technically doesn't have energy. We've never been able to get down to absolute zero, but we've come really close. But the Kelvin temperature scale has the same increments as the Celsius scale, but the absolute zero is 0. So we like to use Kelvin in physics because it's always going to be a positive number, not a negative number. And it's a simple conversion from Celsius to Kelvin. You just add 273.15 to the Celsius to get the Kelvin. So what does this mean? Well, they all have 3 different numbers. Kelvin boils at 373 degrees Kelvin. That's 100 degrees Celsius or 212 degrees Fahrenheit. Absolute zero occurs at 0 on the Kelvin scale, negative 273 on the Celsius scale, and negative 459. So if we start to deal with negative numbers in these formulas, you can see why Kelvin's a little bit more preferred by scientists. So then what does that mean? Well, Mr. Adams said if something's contained, there's going to be an increase in kinetic energy. And so remember that in our last section, we talked about this linear vibration. This spring is not really a spring. It's like a molecular bond or any force or intermolecular force that holds things together. When we increase the energy, the spring gets stretched out more. If we add temperature to an object, then it will expand. So if we want to find the expansion of an object when we add heat to it, which is really a fancy way of saying we're adding energy to it, the kinetic energy causes those bonds to stretch a little more, and the relationship is A, which is a constant for the item, and we call that the coefficient of linear expansion, times the original length L naught times the change in temperature. Now again, the change in temperature should be in Kelvin. So if they give you Fahrenheit, you got to convert it to Celsius and then convert it to Kelvin. Now delta T for Celsius and delta T for Kelvin should be the same, but I want you to practice doing the 3 conversions. Anyways, plug it in that formula. It tells you how much something will expand. Well, if things expand in 1 dimension, then the area would expand in 2 dimensions. In other words, this length would expand and this length would expand. And we would use this formula to calculate the change over the initial. So for area, it'd be 2 alpha delta T, and for volume, it'd be 3 alpha delta T. And that's because we're multiplying that expansion coefficient times each dimension. So area is 2 dimensions, volume is 3 dimensions. And so here's a short list, and this will be in your textbook as well, of common coefficients of linear expansions, alphas. For example, brass expands at 19 times 10 to the negative 6. But if you notice, iron has a higher coefficient, which is 12. Sorry, I'm trying to convert it in my head. It's 12 times 10 to the negative 6. So what you see here is that iron has a much lower expansion rate than brass, which is why these that's why the thermometer curls the way that it does, is because brass will expand quicker than iron. Does that make sense? Okay. So anyways, when you go to do your homework, look at this list. Water is the only thing that acts weird. So things float based on density, and if we look at this density chart of water compared to the temperature in Celsius, obviously it turns to ice at this freezing point, which is 0, and then right around 4 degrees, water is at its most dense. Now this is not how most objects are. Usually what happens is as we cool things off, they contract. Those bonds contract and they get closer together, which means they get more dense. Water does this weird thing where the maximum density occurs at about 4 degrees. So when water freezes, ice is less dense than the water in some cases. That's why ice floats sometimes. Okay, that'll be in the homework. That's why I put that in there. Kinetic theory in gases kind of helps explain ideal gas law. So if I have a container that doesn't expand and it's filled with a gas, okay, those molecules, when I heat up that container or heat up the molecules in the container, those molecules will have more kinetic energy. Translational, vibrational, and rotational. And what happens is these little objects start bouncing more and more, and they hit the sidewalls with more force, which creates more pressure. And the more pressure you have, well, because pressure is related to temperature, so as we increase the temperature, we increase the pressure, so long as the volume doesn't change, okay? So what does that mean? That means that we can take that relationship between the pressure and the volume and convert it in a number of ways. One way that we can calculate that relationship between the pressure and volume is 1/3 times Avogadro's number, or I'm sorry, capital N, which is the number of, let me show you here on the screen here. Getting a little happy here. The number of molecules in a gas. I just modeled what you should do for your homework, okay? And then times the mass times the velocity squared. And RMS is like an average. And so how do we get that? Well, not every molecule is going to be having the same velocity, okay? So the mass and speed are those of the individual molecule can be averaged out sort of by squaring the velocity and then taking the square root of it, which we call the velocity RMS. And so the molecular kinetic energy can be related to temperature. So if I take this formula, do some fancy math, and relate that to the kinetic energy, we can calculate the kinetic energy 1/2 times the mass times the velocity RMS squared, which should be equal to 3/2 Boltzmann's constant times capital T temp in Kelvin. So, for an internal energy of a monatomic gas, which are like the noble gases, they're content being all by themselves, then there's a relationship between the kinetic energy and the relationship between the temperature and the internal energy. So the internal energy U can be calculated in one of these three formulas, which is just a variation of the previous formulas I've shown you. So the kinetic theory of gases also helps us to understand diffusion as a result of motion of molecules. So if I have a porous barrier that has oxygen and CO2, if we increase the temperature, and this was equal volumes of CO2 and equal volumes of oxygen. So this is one way to kind of allow oxygen to filter through but capture carbon. And this is stuff that I've witnessed at Notre Dame, hanging out with the energy group there. Basically, by manipulating the temperature, we can manipulate the pressure. There's a relationship between the mass and the kinetic energy. And so what happens is that the less massive objects are able to pass through the barrier. You still get some carbon that goes through, but if you were to put 3 or 4 barriers up, this is a very effective technique for carbon capturing devices or processes. Okay, and so kinetic energy of diatomic gases in the equipartition theorem says that atoms in a monatomic gas have only translational equilibrium to contribute to their internal energy. But a diatomic molecule, like oxygen always travels in pairs. That's where the di comes from. Diatomic means 2. Hydrogen always travels in pairs. So hydrogen, oxygen, nitrogen, anything that ends in gen. The monatomic are the noble gases, and those always end in on, usually. So like, well, helium's the exception, but like neon, freon, the noble gases. So a diatomic molecule can also rotate because there's the two interlockings of the molecules, and they'll rotate about an axis, the x and y axis. So the equipartition theorem tells us what the contribution of the rotational states is to the internal energy. On average, the total internal energy U of an ideal gas is divided equally among each degree of freedom of its molecules possess. Furthermore, each degree of freedom contributes to the internal energy based on those formulas. A diatomic molecule has 5 degrees of freedom, translation in the x, y, or z, but rotation around the x and rotation around the y. So what does that mean? Well, that means that when we go to calculate the internal energy, we have to calculate the translation plus the rotation kinetic energies, and then we add them up. And there's 2 ways you could do it. You could use this formula, or you could use these formulas. And so depending on the information that's given to you, whether it's the number of molecules or the number of moles, or well, usually that's about it. That's how you would calculate the internal energy. So in summary, we can convert from Celsius to Fahrenheit using those 2 formulas. Heat is energy transferred from one object to another due to temperature difference. Ideal gas law, it says that the pressure times the volume is equal to some variation of the temperature. And there's a variety of ways to do that. Boltzmann's constant is 1.38 times 10 to the 23rd. Absolute zero in Celsius is negative 273.15 degrees, which is 0 Kelvin. To convert from Celsius to Kelvin, we simply add that 273.15. More kinetic energy due to heat transfer is going to cause something to expand. So to find the linear expansion or change in length, we take the coefficient of linear expansion multiplied by the original length times delta T, which should be converted to Kelvin. The results of the kinetic theory of gases means that there's a relationship between the kinetic energy and the temperature, as stated there. For monatomic gases, we could calculate the internal energy by using any one of these three equations. For a diatomic gas, we need to consider the translational kinetic energy in addition to the rotational kinetic energy, and so then we could use this formula or this formula or this formula. And that's it.